Hello, can you hear me now? Hello, can you hear me now? Sorry, I didn't check. Do you think the people can hear me? Okay. Right, sorry about that, but you should have informed me a little bit earlier. All right, hopefully these sort of things don't happen when I get my teaching exam. Okay. All right, I was too enthusiastic. So if x1 is independent of x2, then we have this relationship. The variance is the variance of the sum is the sum of the variances. Of course, this extends to n random variables. Okay, but what if, let's ask ourselves a question, what if x1 is not independent of x2? Then of course this formula does not hold. All right, so now no matter what x1 and x2 are, let us show the following claim, and then we'll use it later on to do some interesting calculations. Now x1 is not necessarily independent of x2, but we have that the variance of x1 plus x2 is variance of x1 plus variance of x2 plus the covariance of x1, x2. This is always true. I'm wrong. It is 2 here. Okay. Before we do any sort of justification, right? Let us see whether this makes sense. Just now I missed a 2 here, and immediately some alarm bells rang in my head. Why? Because I checked in my head. I checked one simple fact. Okay, let's do a check. Suppose x1 is equal to x, and x2 is perfectly negatively correlated with x. So it's minus x. Now, x1 and x2 are clearly not independent, because if I know x2, I know x1 exactly. It's just a negation, right? They are definitely not independent. So we ought to use this formula here. But is this formula correct? If I didn't put the 2 there, something is wrong. Let me show you. So left-hand side is equal to variance of x1 plus x2 is equal to variance of x plus minus x, which is of course 0. Variance of 0, as with a variance of any deterministic number, is 0. Agree? Very good. How about the right-hand side? We have the variance of, well, x1 is x. The variance of minus x. What is the variance of minus x? Alvin G. Variance of minus x. Then we can test whether I'm muted or not. Alvin G. Variance of minus x. Maybe it's not there. How about EE2012A? These people are not responding. I know who will respond. Yes, EE2012A will respond, and EE2012A says 0. Very good. Eh? No, variance of minus x is not 0. Come on. Something is not right. Variance of minus x. How is that related to variance of x? Someone can try to help EE2012A or Alvin G? Exactly. Okay, so we'll keep that for the moment. Plus 2 covariance x with minus x. Okay. Now, last time we said, okay, let me just simplify this. So this is variance of x plus variance of x. Okay. Last time we did mention a particular formula. Let's go to last time. Okay. We mentioned a particular formula to relate covariance of a linear combination. So we have this relationship from last time. Okay. So last time we stated this without proof, but let's say it's believable. Okay. So now we can take our y, we take b to be 0, and we take a to be minus 1, and we take x, we take y here to be minus x. Okay, so you notice that if you use this particular formula, you take x to be x, you take y to be minus x, and a to be 1, b to be 0. Then what you get here is that you have, maybe you take y to be x here, and a to be minus 1. Okay, then what you have is, let me make this look neater. This is -2 covariance of x and x. But do you know what is covariance of x and x? We also mentioned this last time. Covariance xx, that is exactly variance of x. So this is equal to 0. So the point here is that if I look at this special case in which x1 is x and x2 is -x, I get 0 on the left-hand side, and I corroborate the left-hand side using the right-hand side, which is also 0. Notice that if I didn't have this 2 here, something is wrong. So it's important to have the 2. Understand? Alvin, you understand? Can you hear me? Does everyone here understand? Very good. So you check with this particular formula from last time, okay? How we actually employ it, okay? In the context of the above calculation. So the above calculation is plausible. So let's try to do a few little justifications of it, okay? So we still need to justify that formula because we just look at one particular example, which is not enough. So what we will do is the following. The left-hand side is the variance of x1 plus x2, and according to the definition is x1 plus x2 minus expected value of x1 plus x2 quantity squared. It's like this, okay? But this can be written as follows. You group things together, x1 minus expected value of x1, okay? You group this and you group that. Quantity squared, okay? No, this is this here squared. All right, so basically I just distributed this. I marry this with this and it yields this. And then I marry the other people, like this guy gets married with this guy and they form this term here. Okay, so now we recall a very simple formula, which is say a plus b quantity squared is a squared plus b squared plus 2ab. I think we know this. So this becomes expected value of x1 minus expected value of x1 quantity squared plus expected value, the x2 minus expected value of x2 quantity squared. Now these are called the solo terms if you wish, but then we have the cross term. This is the cross term. We have 2 expected value of x1 minus expected value of x1 bracket x2 minus expected value of x2. This is called the cross term, okay? So what we have here, this is exactly the definition of the variance of x1. And this is exactly the definition of the variance of x2. And this is unsurprisingly the definition of the covariance of x1 as x2 as desired. So hopefully it's not very difficult. Does everyone follow? Where did Oliver disappear to? Anyone? Does everyone understand this? Okay, let me go through one more time. The left-hand side is nothing but the variance of x1 plus x2. Okay, the variance has this particular definition. Recall that the variance of x can be written as the expected value of this quadratic function here. That is the definition of variance of x. Now we take x to be x plus x1, x equals to x1 plus x2. So it comes here and the expectation comes here. But because expectation is linear, I can group the yellow guys together and I can group the red guys together. Then what we have is we can treat this as our A and this as our B. Then we make use of this formula here, expected value of A squared plus expected value of B squared plus 2 expected value of AB. Cool? This is now equal to this by definition. So in particular, we have that the final term here, this is nothing but the covariance. This is nothing but the covariance of x1, x2 by definition. Okay? So I have gone through this derivation. I will not ask you to derive these things. I will ask you to do calculations. All right. But before we do a simple calculation, actually not so simple. All right. Let me tell you that this can be readily generalized. This can be readily generalized to n random variables. So the variance of the sum of n random variables, this is the notation, of course, for a sum, x1 plus x2 all the way up to xn. These are the individual terms, the variance terms. And we have the cross terms. The cross terms, of course, involve covariance xi, xj. But the xi, xj are only those i's and j's that are not the same. So by this notation here, this what we mean here is we sum over all possible values of I, then we sum over all possible values of j that are not equal to I, but j runs from 1 to n. Okay, that's the meaning of this notation. It can be a little bit ambiguous, okay, in mathematics. But that's what we mean. We look at all possible values of I, then we go over all possible values of j, but we skip I. Okay, that's covariance sum. So in the case when look, so you see here, right? The astute student among you will say, have you missed a 2 here? Right. So let's verify that this is the case for n equals to 2. When n is equal to 2, the left-hand side becomes variance of x1 plus x2. And on the right-hand side, we have variance of the solo terms. Okay. And then we have the cross terms. Okay, so we are going to run over 1, 2. So we are going to fix x1. Okay, and then we'll run over everybody else except x1. But there's only one body else, x2. And then we're going to fix x2. And then we're going to run over everybody else. But there's only one other person other than x1, other than x2, which is x1. So these two can be combined to yield, because the covariance is symmetric, right? So we can run over this to yield 2 copies here as desired. Okay, does everyone understand this? So it seems like here we are missing something, a 2, but in fact we are not missing nothing. We are not missing nothing at all. All right. Okay, so notice something, right? How many terms are there here? No. There are n terms here. How many terms are there here altogether? Can someone quickly tell me? We will need this in the next example, the next calculation. How many terms here? There. No, nothing to do with factorial. There are how many terms here? No, it's related to n. Elvinci? Because Elvinci is not answering me today. Usually he answers me. How many terms are there here? So in the case when we have 2 random variables, we have 2 terms. Who said n minus 1? You are halfway right. You are thinking in the right direction. Very good. You have, there are n times n minus 1 terms here. Okay. How to see this? There are at least 2 ways I can. Yeah, very good. That's the third way. That's the third way. In my head, there are 2 ways. Okay. They're very good. That is the mechanical way. In my way, okay, we do n choose 2. So from we choose n choose 2 times 2. N choose 2 is n times n minus 1 over 2, and times 2 is n minus 1. Okay, that's one way. That's the combinatorial way. But let me show you another way. So you can place all these covariances and covariances in a matrix. You know matrix? You can put this all in a matrix. And then the variances are on the diagonal. The variances of x1, they are on the diagonal. You don't even know this. Xn on the diagonal. Then how many things are there on the off diagonal? In the off diagonal, we have variance or covariance of xi, xj. How many terms are there in the off diagonal? This is an n by n matrix. So is n squared minus n, because there are only n terms on the diagonal. Okay, and the remaining terms are this. And this, of course, is n times n minus 1. That's the way I look at it. You minus the diagonal. The covariance along the diagonal are exactly the variances which have already taken care of in the first term here. That's the way one looks at it pictorially. I prefer pictures. I don't know about you. Yeah. So this you don't need to know this. Okay. So now I mentioned this can be readily generalized already. So to the n terms. So let's look at an example. All right. This is a difficult example. There are n people who throw their hats. We have seen this example before, and David Woodside was a bit confused. Is he here? There are n people who throw their hats into an urn. Okay, then they pick a hat at random. Each one picks a hat at random. So here there are n students. They all throw their hat. Each one of us has a unique hat. We throw our hats into an urn, and then after the whole operation, we then each one put our hands in and then take a hat. So I may have taken Oliver's hat. Okay, and Liao Xue, you might have taken my hat. But the question we are interested in is X, which is defined to be the number of people who pick their own hat. Okay, so we can rewrite X as X1 plus X2 plus ... plus Xn. Okay, now what is Xi? Xi is equal to 1 or 0 if person I picked his or her own hat and otherwise. So let's say I is David. Then if David picked his own hat, X David is equal to 1. Otherwise it's 0. So basically this counts the total number of people who pick their own hat. And we are interested in the expectation and variance of this particular random variable. Now, the first question you ask, right, is suppose we only have 2 people, n equals to 2. Is X1 and X2 independent? Okay. Suppose there are 2 people and 2 people throw their hat into an urn, right? And I pick my own hat. Suppose the 2 people are myself and Oliver only. I pick my own hat. Did Oliver pick his own hat? Must be yes, right? Because there are only 2 hats in the urn. And if I pick my own hat, Oliver must have picked his own hat. So if you know that X of me is 1, you know that X of Oliver is also 1. Right? So the 2 random variables, X1 and X2, are very much not independent. Does that make sense? So we cannot make use of the fact that variance of X is just the sum of the variances. That is very wrong. Very, very wrong. So we need something more subtle. Right? Because the random variables are in general not independent. In fact, they are far from independent. Do you appreciate this? Oh, so I have so many answers here. Oh, Elvinci finally appeared. Okay. But Elvinci, do you understand that this problem is a bit subtle? Because the point here is that, remark, the random variables xi, I running from 1 to n, are not independent. And hence we need to use a more subtle formula. We cannot use the fact that the variance of the sum is the sum of the variances. Okay, we just have to look at the case n equals 2. But for general n, the random variables x1 to xn are also far from independent. Okay, can I move on? Right, nevertheless, we have that the probability that xi is equal to 1 is equal to 1 over n. There's a 1 over n chance of me picking my own hat. Okay, so the expectation value of x, which is the sum of all these xi, expectation values of xi's, so that's the expectation value. I'll just write it in terms of sum, xi, I running from 1 to n. That is nothing but the sum of the expectations. We have done this calculation before. Here, expectation of the sum is the sum of the expectation holds for any collection of random variables, independent or not independent, whatever. And this is a very deep result that can help us to show many interesting things in theory. Okay. If you take my higher level class, you know that this simple relationship can bring you very far in life. So here you have sum 1 over n, which is 1. So on average, one person out of n will pick his own hat. Okay? But then the next question is much more subtle. How about the variance? Claim, which we need to prove. Variance of x is also equal to 1. So there's a variability of 1. So standard deviation is also 1. Standard deviation is square root variance. That's a formula you need to commit to memory. Okay, so this is a bit surprising. All right, let's look at why this is the case. All right, so what we need to do is to compute the variance of x. We want to use this formula. We need to prepare ourselves to use this formula. Prepare ourselves, okay? Because the variance of the sum is generally not the same as the sum of the variances. So we need to prepare ourselves to use this formula. So in order for us to use this formula, we need to calculate the component variance and covariance, right? So what is the variance of xi? Well, x is a Bernoulli random variable. So its variance is xi squared minus expectation value of xi quantity squared. Okay, so because this is nothing but a 1-0 random variable, so this has the same distribution as just xi. You don't need to square it. Xi quantity squared. So this becomes 1 over n minus 1 over n quantity squared. That's the variance. Okay, so let's try to make it look neater. And we have the variance can be written as 1 over n into 1 minus 1 over n. Okay, so that's the variance of each individual random variable. Now we need to worry about the covariance of xi, xj. Aha, this is a bit harder, I tell you. This book is a bit non-trivial. All right, so the idea here is to use the particular formula, expectation of xi, xj minus the expectation value of xi, expectation value of xj. Okay, so these xi's, xj's are 1-0 random variables. They can only take on the values 0 and 1. So we can rewrite this first expectation as the probability that xi equals to xj equals to 1. Right. Why is that so? This random variable here, the product, can only take on the value 0, 1. So the expectation is nothing but the probability that both xi and xj are both equal to 1. That is the only term that will contribute to the expectation. Now this is then easy, 1 over n quantity squared. You need to understand why this is the case. All right. And I'll justify it here. The expectation of xi, xj is nothing but the sum over all possible values of xi, xj, xi, xj, the probability that xi equals to little xi, xj is equal to little xj. Now, the xi, xj's, they only can take on values 0, 1. So the only term that contributes to this expectation is when xi equals to 1, xj is equal to 1. Okay? That is the case. So this can be decomposed into the probability of xi equals to 1 multiplied by the conditional, because as I said, the random variables xi, xj are not independent. This is by Bayes' rule. Okay? By Bayes' rule. Again, the probability that xi is equal to 1 is 1 over n. Okay? Now, suppose, right? Suppose that one person has got his own hat. This is the meaning of xi equals to 1. We are living in a world that, for example, we have n people here, but Oliver has his own hat. We know that he picked his own hat. There are n minus 1 of us remaining. What is the chance that I pick my own hat? I don't need to care about Oliver already, because I only have n minus 1 other people. And so the chance that I pick my own hat is times 1 over n minus 1. There are only n minus 1 of us left. We are living in a universe where there are only n minus 1 people left. We don't have to worry about the person who picks his own hat. So everyone understand why this 1 over n times 1 over n minus 1. So minus 1 over n quantity squared. All right, and this can be made to look a bit nicer, which is 1 over n squared n minus 1. Cool. So now we have all the ingredients. We have all the ingredients to substitute inside the variance formula. Okay. Here we have a total of n terms, and each of the variances is given by this guy here. Okay. So let me just plug this in here. This is 1 over n into 1 minus 1 over n. And this guy here is 1 over n squared n minus 1. So we can plug this slowly. Because there are n terms here, we have n times 1 over n times 1 minus 1 over n plus. Now, each one of these terms here, they're all symmetric or the same n minus 1 here. Then I ask you the question, how many terms? Yes, Alvin G, very smart. The variance can also be derived by this. Yes. So how many terms are there inside this strange sum here? We answered this question just now. N times. N times n minus 1. You're looking at how many off-diagonal elements there are in the square matrix. You're looking at how many elements there are in the square matrix that are off-diagonal. This is nothing but n times n minus 1. That is the number of terms in here. Each one of them is the same. Here, the number of terms is only n. Okay. And what I'm using here is this number here, which we calculated for the variance, which, as Alvin G correctly said, is P1 minus P. And then finally, this term here is what we painstakingly calculated for the covariance. After you're all set and done, after you have cancelled here in and out, what you get is 1. Okay? So this is a very challenging exercise because the xi's are far from independent. But nevertheless, if we use the formula, we are good. Right? If we use the formula properly, we calculate the covariance of xi, xj, then we are good. We are good in the sense that we can calculate the variance properly. Okay, any questions? Yeah, okay. So this is the case for n random variables. Yeah, but feel free to keep the questions coming, especially next Tuesday. Okay. Any other questions? Here we did for n random variables, but I know what you're thinking about. I know. Because here you see that we seem to only worry about covariance of xi, xj when I is not equal to j. We worry about this. But by symmetry, right? By symmetry means everything is the same. Okay. If for every I not equal to j, the covariance I xi xj must be the same. So I'm just calculating one generic term here. I'm just calculating one generic term here, and then I'm multiplying by the number of times I sum up. It's just like I sum the number 2n times, I get 2n. Right? We only have to worry about pairwise, the pairwise correlation. Okay. Yes, actually not quite true. You can talk about covariance for n random variables also. Then it becomes a matrix. Right? Okay, let me move on. All right. So now we are going to talk about section 4.3. Okay, we have finished section 4.2. I will skip section 4.4. All right. We don't really have to talk about moment generating functions. But the next time this class is offered, I will need to talk about it if I'm still around. Okay, so let me talk about conditional expectations and condition. And next time we'll talk about conditional variances, which conditional variances, the topic of next Tuesday, is the hardest thing you will come across in this class. Okay, conditional expectation is perhaps not so difficult. Conditional variance was what I found most difficult when I took this class, maybe about 18 years ago. All right, let us recall what we mean by conditional expectation. Okay, right. You have seen this before. Given two random variables, x and y, all right, the conditional expectation of the random variable x given the event y equals to y. So y equals to y is a particular event, is given by expected value of x given y equals to y. It is defined to be two cases, sum over all possible values of x, xp, x given y, if x is discrete and the integral x, this is the conditional PDF, x given y, dy, if x is continuous. That's my short form for continuous. Okay, so actually we have seen this before, and I think you have also done some exam and homework, quiz and homework problems. Right, but the next thing I'm going to say is perhaps the hardest, one of the hardest things that you will come across. Okay, this is the first thing I talk about when I talk about when I teach my graduate class in probability. Okay, everyone is expected to know this. Here we are talking about the conditional expectation of x given an event. All right, the next thing I'm going to talk about is the conditional expectation of a particular random variable x given another random variable y. Okay, no, so notice that the language is different. Here we are given an event. Here we are given another random variable y. Okay, is the random variable denoted by expected value of x given y that takes on the value y, little y, that takes on the value, the value expected value of x given y equals to y, when y takes on the value y. Okay, this sounds like a mouthful, all right? This sounds like a big mouthful. But here what we are defining is the conditional expectation of a random variable given another random variable. Okay, in order for us to understand this, we need copious amounts of examples. Okay, and the book actually provides 3 or 4 examples. I'll provide a few more. Okay, so let us consider the following simple example. Let's consider a bias coin whose bias y is uniform on the interval. It's uniform on 0, 1. So what is the meaning here? You have a coin, but the probability that it produces 1 is itself a random variable that is uniform on 0, 1. So before you toss the coin, some random number generator generated y. Then that y is fixed, and then you toss a coin with bias y. Understand? There are 2 sources of randomness here. One source of randomness is what is the bias of the coin. The bias means the probability of hit. The probability of hit is itself a random variable and is uniform on the interval 0, 1. Next, once you fix the probability of hits, which is capital Y, you're going to toss a coin a few times, and then you will ask a few questions. Okay? But before we ask a few questions, let's try to understand the notations first. All right? So we're going to toss, after we have this bias of capital Y, we toss the coin n times and let x be the number of hits. Okay, so what is the range of values of x? What values of x can take on? 0 all the way to n. Right? You can have 0 hits, you can have n hits, you can have a few hits in between. You cannot have 3.5 hits though, all right? Because x must be integer valued. Okay, so what is the x? Let's try to understand what is the expectation value of x given that y is equal to y. Suppose that the random number generator told us that the capital value, the capital Y is equal to 0.2. Say the bias of the coin is 0.2. Then what is the average value of x? The bias of the coin is 0.2. What is the average number of hits that you will get in n tosses? Yes, very good. Then this will be 0.2n. But more generally, all right, do you agree that this is n times y? Here, y is a number in 0, 1. So For every little y, say 0.2, the conditional expectation of x conditioned on the event is 0.2 or y times n. Right? Because if I have a coin and the outcome and the probability of head is 0.9, then I expect to have 0.9 n heads in n tosses. Just like Liao Xue said, if y is 0.2, then the expected number of x's, number of expected number of heads is 0.2n. Clearly. Okay. Now, this is conditional expectation given an event. Y equals to y. Now, the conditional expectation of x given the random variable y is thus expected value of x given y no more equals to little y, no more, is exactly n times capital Y. So the conditional expectation is the hardest thing you'll come across in this class. The conditional expectation of a random variable given another random variable is itself a random variable. Okay? Even people in my graduate class cannot fully get this. So the first expectation there is conditional expectation of x given event. The second one is conditional expectation of x given another random variable. So you replace the little y here and the little y here by capital Y. Okay? But y equals to y, here we are going to simplify to y. This one we have n times capital Y. So the random variable, the conditional expectation of a random variable given another random variable is a random variable. Okay? Thus, the conditional expectation of x given random variable y is thus the random variable given by this. Okay? Thus, we can ask ourselves the question, what is its CDF? What is its CDF? i.e., what's the CDF and the PDF, if you wish, of the random variable expected value of x given y? Okay, maybe we can give this a name. Let's call it Z. So fz of z, we have done this exercise is, okay, we always write down, I can give you some compassionate marks if you write this down, z less than z. Okay. Now this is nothing but probability. What is z? Z is exactly n times y because the conditional expectation, we give it a new notation z. And you notice right here, z is n times y less than z. This is equal to the cumulative distribution function of y evaluated at z over n. Okay, I skipped one step, sorry. This is equal to probability y less than z over n, right? So the two cumulative distribution. Yes, Alvin G, you are absolutely right. The expectation is no longer a number when we condition on a random variable. It took me about 10 years to fully understand this. Okay, so hopefully with better teaching, it will only take you 10 minutes. Okay, because the person who taught me this, oh my gosh, I don't know, right? So now we can actually have the CDF and we can find the PDF using the same procedure as in the tutorial. Okay, by the way, here before we do anything, y is uniform. I did say that y is uniform on 0, 1. Okay, y is uniform. So the PDF, the CDF here looks like z over n. Okay, because we are uniform. And here z can only take on values from 0 to n. Okay, because y takes on values from 0 to 1, z is a scaled up version of it. It can take on values from 0 to n in this range here. And the PDF of the conditional expectation now is nothing but 1 over n when z is between 0 and n and 0 otherwise. So this is the PDF of the conditional expectation. I know there are many concepts. So here is n, here is 0. That is the PDF of the conditional expectation. Z is the conditional expectation of x given y. And it looks like this. It's flat. And because it is induced by y, which is flat. Okay? Right, this is the first of many examples. So one more time, I will spend 2 more minutes to talk about this example and then we'll take a break. The conditional expectation of x given a random variable is a random variable. As Alvinci said, it is no longer a constant. Now, in this experiment, there are 2 things that are happening. First, I'm generating a bias. Why? The bias is itself uniform on 0, 1. Now, after the bias is generated from MATLAB, okay, you generated a random number from 0, 1, you are going to toss a coin with that bias n times. All right, what is the conditional expectation? If I know that the bias is little y, okay, we fix a particular number, say 0.2, then the conditional expectation of the number of heads is 0.2 times n by mental calculation. So we have, in general case, n times little y. Then what we are going to do is we are going to put random variable, we are going to replace this one here, oh, sorry. We're going to replace this one here with the capital Y. So we have this. And we're going to replace this with the capital Y also. But we don't usually write, no one in the world will write actually expected value of x given capital Y equals to capital Y. We just compress this to Y. That's why you see a Y here. So now we created a new random variable, which is the conditional expectation of x given Y. And it is a function of Y. This function of Y is a very simple function. It's just multiplied by n. Okay. And using the same procedure, we can give this a name Z. Okay. We can simply find the PDF of Z, which is basically a flattened version of the PDF of Y. Because the PDF of Y is like this, is 1, the PDF of Y is like this. Okay, that's the PDF of Y. Then, because we toss it n times, it gets stretched out like this. Okay? Right, so now we will take a 15-minute instead of a 10-minute break. What is the additional 5 minutes for? For you to fill in the student feedback. Thank you very much. Okay, so the people in Zoom also can do the same thing. All right, if the people here don't have computer, that's an excuse. You can use mine. All right, so we will come back at 3:01. Okay, and please ask me to start the recording. Okay, thank you very much for those who have done it. It's very much appreciated. So let us continue our discussion of conditional expectation, which is a difficult concept. All right. So we have done one example to illustrate conditional expectation. Let's try to understand it more. Since the conditional expectation of a random variable given another random variable, expected value of x given y is a random variable, okay? It has an expectation, which is a number, all right? So if we have a random variable, then it has an expectation. In fact, next time, we will see that it has a variance as well. Has a variance. And we will find out what is its variance in explicit terms next time. Okay, so what is the expectation? That's an easier question. So we have a certain random variable expectation value of x given y. We are allowed to take its expectation, all right, this way. Now, what do we mean by this particular expression here? Okay, if y itself is discrete, then we are doing an averaging over y. Here's the PMF of y. And we are taking the expectation value of x given y takes on the value y. All right. So you can think of this quantity, right? You can think of this as a function of y, g of y. And when you're looking at expectation value of g of y for the discrete case, what we are doing is just p of y, the PMF of y, times g of y. And so what we have here is that this quantity, we can regard it as a function of y, g of y, and it's here, and it also appears here. And the averaging is done only over y. Can you see? Everything is consistent. Now, in the case when y is continuous, then we will just integrate over the PDF of y, expectation value of x given y equals to y. We need to dy this, okay? But these quantities here all reduce to the expectation value of x. Both expressions, okay, on the right-hand sides, are equal to nothing but the expectation value of x. Okay, so let us verify this for the continuous case. Let's verify this. So we start from here, okay, and we ask ourselves the question, is this just the vanilla expectation value of x? Okay, so let us try to integrate this from minus infinity to infinity. We keep this here. Okay, what is the meaning of this expectation? This expectation is nothing but the integral of x times fx given y, x given y, dx, dy. All right, so this part here, this is the conditional expectation. We are writing it out in its full glory here, in its full form. Okay, we are integrating over the conditional PDF of x given that y is equal to little y. Can you see that? So this comes from the previous formula, and I will not belabor the point. Okay, so at this point in time, we can do a few things. You know that this integration is integrating over y. This is integrating over x. So we can actually swap. Now in signals and systems or something like that, right? Or 2023, you'll always swap this, I know. So we can bring the x running from infinity to infinity outside and bring the x outside, and y running from minus infinity to infinity inside, f of y, y, f of x given y, x given y, and we change the order of the integration. That's what we always do in electrical engineering. But there's a justification as to why we can do it. If there's any math minor here, you would know that there's something to show here. There's some non-trivial, you cannot always swap two integrals like that, especially if they are going from infinity to infinity like that. Cannot, right? The math people will be very upset. But here, okay. Right, so now we can retain this x running from minus infinity to infinity over here. This can be simplified to the joint by base rule, dy, dx. But the inner integral is nothing but, because we are integrating out the y, we are taking out the y here, we are integrating out y, so we are left with only x. This is the marginalization operation, and we recover expectation value of x. So the expectation of the conditional expectation recovers the expectation. This has a name, okay? This has a name and is super important. It's called the law of iterated expectations. The expectation value of x can be written as the expectation value of the expectation value of x given y. The law of iterated expectations is very strange, all right? But Alvin Chi mentioned that the conditional expectation is no longer a constant. That is the point. It is now a random variable. For a random variable, we can take its expectation and we can ask, what is the expectation? Well, it is nothing but the original expectation of x. Okay? Yes, very good question. Can you iterate for many, many times? Can. That is a subject of some future class, all right? So generalization. Liao Xue is generalization. Okay. Expectation value of x can be, you can do the following. X given y and z. Condition on z like this. Oh my gosh. You don't need to know this. This is a little bit involved, okay? But this is an expectation because we are conditioning on two things. All right. Here we are fixing a z. This is another. This part here is another. Okay. This itself is a conditional expectation, a random variable, a function of z. Now one more time, then we get a number. That's why if you learn higher what do you call that? Stochastic processes and a bit more advanced probability, this has a name. That is not law of iterated expectations. People call this in the math sense tower property. If you go Wikipedia, you can find tower property. Why is it called tower property? Because this looks like a tower, like a pagoda. There are many layers, right? Now, this is very abstract at this point in time. So we need to illustrate all this with many examples. Let me illustrate this with a particular example that continues from the previous one. Okay, even if you don't understand why this is the case, you need to understand how to use it. All right. So let's consider that particular example in which y is uniform on 0, 1, and x is the number of heads of n tosses of a coin with bias y. Okay, so that was a continuation of the previous example. So in the previous example, we showed that the expectation value of x given y is what? Is actually n times y. Okay, so let me ask everybody, including Liao Xue, one more time. If y is equal to 0.2, okay, so the coin has bias 0.2. How many heads do I expect? I expect 0.2 times n heads, right? Of course. So if the probability of heads is capital Y, then this is also capital Y here, multiplied by n. Okay, so now let us try to use the law of iterated expectations to find the expected value of x, the total number of heads in n tosses of a coin with random bias. So we are taking the expectation value of x given y. This is nothing, the inner random variable is n times y. Okay, n can be brought outside. What is the expectation value of y? Y is a uniform random variable on 0, 1. Elvinci, what is the expectation of y? Half. Perfect. N over 2. So you see, in this question here, right, there are two sources of randomness. One source of randomness is the random bias of the coin. The coin itself is biased, but the bias is random. No one says that the coin is fair. No one says that the coin has bias 0.2. Its bias is random, but the random bias is uniform on 0, 1. All right, now you're going to toss the coin n times, and the expected amount of heads you get is n over 2. It takes into account two sources of biasness. Understand? No? Okay, let's try again. So before you toss the coin, the bias of the coin, that is the probability of heads, is a random variable that is uniform on 0, 1. Okay, so here you have a coin, and the bias of heads, the probability of heads is y, where y is uniform 0, 1. Now you're going to toss this coin n times. How many heads do you expect to get? Before you toss, the bias is determined by a computer, and it's a random number from 0 to 1. Okay. After the bias has been determined, you're going to toss the coin n times. On average, you're going to get n over 2 heads, which is like an average of an average. Okay. What is the random variable y? Y is uniform on 0, 1. So this is the PDF. This is the PDF of Y. What is his expectation? Vinci said half. Because if we put a wedge here, the whole PDF is balanced. If you have a uniform random variable, then the expectation is middle, right? So we can actually perform this calculation. The expected value of Y is integral of Y dy. Actually, you need to times 1 from 0 to 1, and this is half. Okay, there are two sources of randomness, remember. Okay, right. Now, we have seen actually the next example in a tutorial, okay, but I will repeat, okay. Example, we have a stick of length L. So this is our stick. All right, we have mentioned this in the tutorial, at least in my tutorial. Now, we are going to break it uniformly at random, at a uniform point. And the left part has length. Of course, it's going to be a random length. We're going to call it Y. So we broke it. Maybe we break it, we are very generous, okay? We broke it and the left part is still pretty long, okay? So that's just a realization. It's not halfway, huh? Not necessarily halfway. Then we're going to break it again. And the left part has length X. So we're going to break it again uniformly at random with total length Y. So here, this is all aligned. This is our remaining piece. Okay, so we are going to break this at some point. Oh, we broke it here. Now, in the remaining piece, we break it uniformly at random. We break here. That's just the outcome of my experiment. So what is the expectation value of the last piece? Okay, that's what we're going to find. In the tutorial, we use a very circuitous way to find this. Circuitous means long-winded. All right, so we are going to use a short way to find this. All right, so let us see. Okay, what is the expectation value of X given Y equals to Y? What is the meaning of this? That means that the first break, right? The first break is known to result in a stick on the left-hand side of length little y. Then what is the expectation value of X? Okay, so now we know for sure that this part here, this length here is little y. Little y is known already. Say it's L over 3. What is the expectation value of maybe 2L over 3? Say, we know that the first break resulted in the length of the stick being 2L over 3. What is the expectation value of X? We are breaking the remaining stick uniformly at random. What is this? If this is 2L over 3. We are breaking X uniformly at random from this part here. Very good. L over 3. Yeah. So more generally, this is gonna be Y over 2. Agree? If I know that the intermediate stick is of length little y, the expected value of the next break, which is this, is going to be little y over 2. So in this particular case, it's going to be L over 3, but let's consider the general case, okay? Let's remove this. So what we have here, this implies that the random expectation X given capital Y is Y over 2. Okay? So now, by the law of iterated expectations, this is expected value of, you put in this random variable X given Y. This is expected value of Y over 2. Right? You can take out the constant half and you're left with expected value of Y. What is the expected value of Y? Well, you're breaking from the first stick uniformly at random. So the expected value of Y is nothing but L over 4, L over 2. So this is half times L over 2, which yields L over 4, which corroborates our intuition. We break 2 times, the the leftmost stick is of length L/4 on average. Cool, right? No one told you this before, right? Very cool. Okay. So this is yet another example. Now, this next example is from the book and it's kind of long-winded and there are many symbols. Let's try to do it, okay? This actually illustrates a point. There are many symbols here, so you might get a little bit confused, okay? But nevertheless, I think it's not a bad example, okay? This is yet another example for us to use the law of iterated expectations. So a class has n students. This book is very Americanized, all right? So I'm going to make it Singaporean, this example. The quiz of student I, the quiz score of student I cannot spell, student I, where I is a number from 1 to n because there are only n students, is xi, okay? So for example, Valencia did very well, all right? The quiz score is 29 out of 30, that's xi, okay? But, okay, the students are divided into k tutorial groups. Oh, okay, just like us, we are divided into supposedly 3 tutorial groups. So let me say 3 tutorial groups, I'll keep it simple, okay? A1, A2, A3. And just like in this book, right? The tutorial groups that we have are disjoint. You cannot be in 2 tutorial groups. And everybody has to be in at least 1 tutorial group. In theory, because I know that everyone gravitates to me. So the point here is that AI intersect AJ is nothing. And A1 union A2 union A3 is the full set. That means that the A's form a partition of the class. Okay, just like us, we have 3 tutorial groups and each one of the tutorial groups has a certain number of students. Okay, and 1 student cannot be part of 2 tutorial groups. So that means that the tutorial groups are pairwise disjoint. Okay, so now let's consider the following, okay? Let's say that we have NS students in tutorial group S equals to 1, 2, 3. So there are 3 tutorial groups. Now, the 3 tutorial groups don't have to have the same number of students. For example, right, if the total number of students in our class is 50, then the number of students in each tutorial group cannot be the same. I cannot cut the student into 3 because 50 is not a multiple of 3. All right. So NS students in tutorial group S, and S runs from 1 to 3. All right. So what is the sum of NS S running from 1 to 3? Can you tell me? This is a symbol. This is what is a symbol. All right. Very good. And so you understand the story. So that's the sum of all the students. I look at all the students in tutorial group A, tutorial group B, tutorial group C, I add them up. Cool. Right. This is the story. Okay. And well, there are certain scores. So the average score, average quiz score of all students, let's say is equal to A, all right, which is 1 over n, sum I running from 1 to n of xi. Oh, that's some score that I'm very interested in. I want to know whether my quiz was too difficult or not. So if this number is above 20 out of 30, I'm okay. Well designed. Okay. Now, we can also look at section. We can also look at the tutorial. The average score of all students in tutorial group S, which is 1, 2, 3, is say AS, 1 over NS, sum over I in AS of XI. So I'm looking at all the scores of the students in tutorial group S, and I'm averaging that. Is that clear? So how are all these related to this? So these are the tutorial group scores. Okay. So for example, I have 3 tutorial groups. These are my 3 tutorial groups, and the scores are okay. This tutorial group has score. This tutorial group has score. This tutorial group only has 2 people, and their scores are 15 and 30. Okay, so basically there is an average. Very difficult for me to calculate the average, but here the A1, the average here is 21. Here the average here A2 is maybe I make it simple for myself. 20, 20, 26. Then I know it's 22. Okay, and here let me make it easy for myself. A3 that is equal to 23. Understand? So those are the tutorial averages. The quiz, the average of the scores of the students in each tutorial group. Okay, and then there's a total, there's an A, which is something that you have to add up these 7 numbers and divide. Okay, something. All right, so I'm not going to do that because I cannot do that in my head. Okay, so those are the average score of the students, average scores of the students in tutorial group S. All right, how is this related to conditional expectation and the law of iterated expectation? Okay, can we compute the average score of the whole class in a different way? Average score of the whole class. The average score of the whole class can be computed in this particular way also. We sum over the number of students in tutorial group S divided by the total number of students times the average in tutorial group S. 3 I equal S equals to 1. Okay, so this is a weighted average. Okay, weighted average. So let's see, this is equal to sum over 3, S equals to 1, N over NS over N times 1 over NS sum over I in AS of AI, XI. Because this is nothing but the definition of the average of the students, average of the scores of the students in tutorial group S. The same thing. Okay. Now you notice then this will cancel with this, and you can bring the N outside. This becomes 1 over N. And now we have sum over all the tutorial groups, sum of all the students in tutorial group S, XI. But this double sum, you're summing over all tutorial groups. And then you're summing over all students in each tutorial group. So this is summing over all possible students, right? Xi. So this is A, which is the average score of all 7 students. All right. So here I'm looking, here basically this ratio here, right? This ratio here is actually 3 over 7, 3 over 7, and 2 over 7 in my example. Understand? Because there are 3 students in tutorial group 1, 3 students in tutorial group 2, and 2 students in tutorial group 3. Understand? It's a weighted average. Okay. Now, how is this related to conditional expectation? Conditional expectation. All right. So let now X represent the score, the quiz score of a student picked uniformly at random. Okay. Let's X represent the score of a student picked uniformly at random from the whole class. Okay, so X is basically this with probability 1 over 7. It's basically 20 with probability 3 over 7. It's probably this number with probability 1 over 7. This number with probability 1 over 7, and so on and so forth. Okay, X is the score of a student picked uniformly at random in the class. And let Y be the tutorial number of a randomly chosen student. Yeah, 8, sorry. 3 plus 3 plus 2, how much? 8, right? That's because I cannot add. Thank you very much. Okay, let Y now be the tutorial number of a randomly chosen student. Okay, so the expected value of X is nothing but A, which is this calculation here. Okay, it's nothing but the expected value, it's nothing but the average of all the students in the whole class. All right, but what is the expected value of X condition that I pick the student from tutorial group S? Okay, this is the expected value of the score of a student when I know that the student comes from tutorial group S. Now this is nothing but 1 over NS, number of students in tutorial group S, I in the student in the tutorial group S, Xi. Okay, this is defined to be A sub S. So this is, suppose Y is equal to 1, I'm averaging the students here. Suppose Y is equal to 3, I'm averaging the scores of the students here. Understand? Okay. So now a randomly chosen student belongs to tutorial S with probability of Y equals to S, which is the total number of students in tutorial group S divided by the total number of students, right? So here S runs from 1 to 3. Okay, so we have the expectation value of X, which is the average of the scores of all the students in the whole lecture, that is equal to A, which is by the definition of conditional expectation, is just this iterated expectation. Here, the outer expectation is averaging over the tutorial groups S running from 1 to 3 of the probability of Y is equal to S of expectation value of X given Y is equal to S. This is nothing but S running from 1 to 3 of NS over S over N. So this is the probability that a student belongs to tutorial group S. Okay, and this remaining term here is the average score of a student in a particular tutorial group, that is A sub S. So the point here is that averaging over tutorial groups can be viewed as a special case of as a special instance of the law of iterated expectations. Okay. Right. So let me go through this example one more time. Okay. We have a class of N students, just like us. All right. We have, say, 8 students here, and they are split into 3 tutorial groups. The tutorial groups need not be of the same size. Actually, not same size, then it's interesting. All right. And within each tutorial group, there are a few students, and you can see their quiz scores here. All right. So there is an overall average score of the students in the whole lecture. So that will be averaging over these 8 numbers, it's some number. How can you compute the average of the students' quiz scores just based on the sub-averages within each tutorial group? All right. So here the sub-averages within each tutorial group are given 21, 22, 23. How can you compute the average of all the average score of the students in the whole class? Okay, well, you will do the following. You will take 3 8s times 21 plus 3 8s times 22 plus 2 8s times 23. Whatever that number is the average score of all the students in the whole lecture. But this is a special case of law of iterated expectations. Because these numbers here, they are the probability that a randomly chosen student belongs to tutorial group A, tutorial group B, tutorial group C. And these are the conditional expectations of the quiz scores of the tutorial of the students in tutorial group 1, group 2, group 3. So in particular, this is the probability. This one here is the probability that the tutorial group is 1, probability tutorial group is 2, probability the tutorial group is 3. And this number here is the conditional expectation of the quiz scores given that the tutorial group is 1, and so on and so forth. Is this clear? The rest of the calculations are just mechanical. This is the essence of the law of iterated expectations. Is the essence. Based on his tutorial group. Yeah. And then average over tutorial groups. Instead of averaging over students, we do sub-averages over tutorial groups first, then we do a weighted average of the scores based on tutorial groups. Note that here we need this 383828 because this group has fewer students. So we place less weight on it. All right. Suppose this group has a lot of students, say 100 students here, then it has more influence, right? So that is reflected by this coefficient here. Understand? Anyway, so this is law of iterated expectations. Next time we will talk about variance, which is a little bit more complicated, but let's end off today's lecture by one last example. Okay? Any questions? This last example is also very interesting, a very interesting story, because I like to ask exam questions based on these sort of things. All right, this is the first quiz question on my graduate class probability. Okay, because everyone is supposed to know law of iterated expectations. Example. Oh, by the way, this example is not in the book. I made it up. Okay, not in the book. You can copy or you can just listen. There are n students. Capital N means random variable who come to class each time. There are n students who show up to LT7 each time. N, well, n is a geometric random variable with probability of success 1/10. Okay, so that means that probability that n is equal to n is 1/10, 9/10, n minus 1. N runs from 1 to so on and so forth. So actually, I could have, in principle, I could have many students. There could be a positive probability that there are 1 million students who show up, because the support of this random variable is on the natural numbers 1, 2, 3, all the way to 1 million, and so on and so forth. This is not the case for our class. We have only got 50 students. Okay, but nevertheless, let's look at this particular example. Just like our class, a random number of students show up each time. Sometimes only 3. Sometimes, like today is a fine day, 10 people show up. Very good. Okay, the story is as follows. Okay, if a student shows up, if a student comes, she or he brings along XI dollars to the class in cash. Okay, and XI is a random variable with mean 7. So he or she brings a random amount of money to class for some reason. But everyone brings some money. The expectation of the amount of money that you bring is $7. I came up with these numbers. So what is the total amount of money? What is the question is, what's the expectation of the total amount of money brought to LT7. Oh, let's assume that the professor brings no money. Okay, so there are two. Liao Xue, do you realize that there are two sources of randomness here? One is a number of students could come. The more students come, the more money generally. Another one is each student brings a random amount of money. Okay, so there are many sources of randomness here. But what we are interested in is S, which is x1 plus x2 plus ... plus x capital N, where the capital N there signifies that the number of students who show up is random. And I want the expectation value of S. How do I do it? We use the law of iterated expectations. Okay, does everyone understand the question? You all can okay, you see, on Tuesday, right, there were only 3 students who show up. Today, you look at around you, so many students show up. So the students who show up to LT7 is a random variable. We model that using a geometric distribution with probability of success 1/10. Okay, so today 10 people show up. Yesterday, 3 people. It's a random number. And then everybody brings a random amount of money. Everybody brings xi, where xi is a random variable with mean 7. On next time, all right, what is the total amount of money brought to the lecture theatre? It depends on how many people show up, right? It depends on how much each person brings. Yeah. So Oliver, you understand the story? There are 2 sources of randomness, at least 2. So let us do a computation. We are interested in the expected value of S. S stands for sum. Okay. Now, what do we condition on? We condition on N, which is the number of students who actually come. Because if I know that the number of students who come is little n, that is very easy for me to figure out how much money was brought in on expectation. So let's look at this. Let's look at expected value of S, given that I know that little n students show up. Okay. Oh, by the way, I forgot to say this. This is independent of the number of students who show up. So it's not like, oh, a lot of people show up, then everyone brings more money. Everyone brings the same amount of money. Each person brings the same amount of money, regardless of how many people show up. Okay, that's the meaning of independent of the number of people who show up. Okay, so what does this mean? This is expected value of x1 plus ... plus xn, condition on n being equal to little n. I know that there are little n students who show up. We know that n students showed up today. Okay, we know for sure that n students show up. So we can actually simplify this whole thing here, because now we de-randomize one thing. We made one source of randomness fixed. So now this becomes little n. Okay, I know how many terms there are in the sum. It's no longer a random sum anymore. So I know that capital N becomes little n because I'm living in that universe that n is equal to n. But because I said that they are independent, I can drop this because of independence. Okay. Now we have all these random variables and we can use the linearity of expectation. And what is this? Elvinci, are you still with me? What is this number? I know that there are little n students who show up. Anyone wants to help Elvinci? I give you a hint. You need to use this number here. Every student brings on average $7. I know that exactly little n students show up. 7n. Thank you. Because each one of these guys is 7 and there are 7 terms. Each one of these guys is 7 and there are n terms. 7 times n. Because here, every expectation is 7. Because I said so. Because I know how much you have in your wallet. Understand? So now I de-randomize. I fix the number of students to be little n. Okay? Got it? So now, in conclusion, we have expected value of the sum condition on n equals to n is 7n. This implies that expected value of s given the random variable n is 7 capital N. All right, I'm just replacing the little n by capital N. Right? We always condition on y, but I can call it n. All right. So now by the Tower property or the law of iterated expectation, I will use this formula here. Okay. And I know that the inside is 7n. Okay. The 7 is constant, can be brought outside. Okay. Now, the only source of randomness is the number of students who show up, which is n, capital N. But I know that capital N is a geometric random variable with probability of success 1/10, geometric. So the expectation value of such a thing we have evaluated before is 1/p, okay? And p is 1/10. So 1/p is 10, okay? So this becomes 7 times 1/p. The p is the probability of success of the geometric random variable and this is 7 times 1/1/10, which is 70. Understand? So a random number of students show up. Every student brings a random amount of money. So what is the total of money that was brought to the class? It must account for the random number of students as well as the random amount of money that each student brings. But that's why next time, very good. Next time we will study the variance of the amount of money that people bring. So this is just the expectation of the total amount of money that people bring. Next time, we will study more things. The variance of the amount of money that people bring to the class. Given that there are 2 sources of randomness, the number of people that come is random, the amount of money they bring is also random. Very cool, right? You never learned this before, right? Very cool. It's quite deep, so I can see that people are thinking, which is good. This is very deep. We can do a lot of interesting things with this. And this is where I will stop today. And I thank you very much for your kind attention. Have a very good weekend. Yeah. And Alvin Chi, you are correct. Thank you very much for your kind participation. Okay, take care, and I'll see you